Very nice introduction. I'm going to talk about visual localization, some recent developments in that area. So I think 30 minutes is planned. I'm not sure how you want to do it. If there are any questions in between, feel free to interrupt me and ask them, because I think there's 30 minutes also for discussion. Whatever works best for you. I have tried to keep it more higher level. If there are more detailed questions, we can either do it here, or if it turns out to go into too much detail, we can take this offline. Good. So visual localization is a problem where we're given an image, and what we would like to do is we would like to compute the exact position and orientation from which this image was taken in the world or in a scene. And often we will use some 3D model of the scene. So what we would like to compute is the position from which this image was taken and the orientation, which is denoted as this pyramid, where the peak of the pyramid is position of the image, and the base gives you the image plane. Why is this an interesting problem? Visual localization has many applications. One of them is robotics. This is a Horizon 2020 project that I was involved in when I was at ETH. And the goal was to build a gardening robot that can cut roses, as you see here, and trim hedges. And that requires that the robot knows where it is in the garden so that it can navigate to its target location. Another interesting application is augmented reality. So here the goal is to enhance the view of the user by projecting virtual content in a seemingly realistic manner into the field of view of the user. So on the right, you see Google's AR navigation that was, I think, last year included as a standard feature in Google Maps for Android devices. And what happens here is that the user lifts the phone based on images. The phone figures out where it is in the world, and then the application draws navigation arrows into the field of view of the user. The same techniques are also applicable to virtual reality. This is a master thesis that I supervised at ETH, where we built like a Minecraft-like virtual world, which was based on the real world and was co-registered with the real world, meaning that I could walk through this virtual world by walking through the real world. That worked quite well, but you just saw me bumping into the chair there. And the reason for this is that we built a static scene. And we could basically just track the movement of the user based on the movement of this heads-up display that the user is wearing. But we couldn't model interaction. And we couldn't also model the rest of the this is something that we tried to address last year. And this is a paper that Joseph mentioned that was shortlisted for Best Paper Award at CIIRC, where we are trying to track the body motion of a user in a scene. The way that this is done is that we are having a head-mounted camera, which we use to figure out where the user is in the scene. And then we have IMU sensors that tell us about the location of the joints of the body, which gives us the human pose. And by combining reasoning about IMU measurements and the camera, we can figure out the motion of the user in the scene without any external camera tracking the human. So we can all do this from the perspective of the user, which makes this much more scalable. So in this talk, I will focus about the localization part. And let's define a bit what we have as data. So the most basic information that we assume we have is what is shown here, where each red pyramid here corresponds to a single image. For each image, we obviously know the image, but also the position and orientation from which it was taken in the scene. Some methods will also require 3D geometry. So for example, a sparse point cloud of the scene, but this is something that in most cases can actually be computed from the images. So images with known positions and orientations are really the basic input to it. In terms of how to do localization, there's like a wide range of techniques that can be used. I'm going to focus on a few in this talk. And I'm going to distinguish between two representations. One is image-based, where the simplest representation that you can think of is based on image retrieval. So you have a set of training or database images. For each image, you know the position and orientation from which it was taken. And if you have a new image, you essentially try to figure out what's the most visually similar database or training image to this new image, and then approximate the position and orientation from which the query was taken by the position orientation of this retrieved image. That's the most basic system that you can think of. Slightly better is, rather than taking the nearest neighbor that you get from the retrieval step, you find multiple nearest neighbors and then do some interpolation between their positions and orientations based on visual similarity to the query image. And that those techniques have the advantage that they are easy to deploy. You just need to compute some sort of image descriptor per image, and then do nearest neighbor search in this descriptor space. But of course, they're both approximate. A couple of years ago, someone had the idea that rather than like doing retrieval or build a more complicated pipeline, you could just train a CNN that takes an image as input and regresses the position and orientation from which it was taken, which in theory has the advantage that this can be computed very efficiently in a few milliseconds because it's just a forward pass through a neural network. And we had a look at this, and it turns out that this technique is actually not working very well if you're looking for accurate camera poses. So camera pose regression techniques can all follow the same approach. You take your input image, you feed this through a neural network that extracts a set of features. You embed these features as a vector in some higher dimensional space. And finally, you project from this higher dimensional space in the space of camera poses, meaning you project in the 3-dimensional space for positions and a 3- or 4-dimensional space for orientations, depending on how you represent it. So let's look at these last two steps, the embedding and the projection. This projection is essentially the last layer in the neural network. And so what you have is you have your embedding, so high dimensional vector that you multiply with some matrix and then potentially add a bias to. And the output of this is like a vector describing the position from which the image was taken, the vector describing the orientation of the image, meaning you can understand this projection matrix as a couple of rows where some of them encode information about the position of the image, the other of the orientation or rotation. And like simple math is that the final pose is essentially a weighted combination of the columns of the projection matrix plus this bias to. So what the predicted camera poses is essentially a weighted combination of a set of what we call base poses. So the network learns a set of exemplar poses that can then be combined to make a prediction for a new image. And this can lead to a couple of problems. So here is a counterexample where you can get pose regressors to fail. So this is like a street close to the dancing house in Prague. And we took a set of training images looking at these facades on one level, and then there's a ramp going up from the river where we took testing images. And you can visualize what the network learns. So here is what you see here is the test or query image. Here you see a top-down view of the camera positions. These are the training poses. This is the positions of the test poses. This is the current, the pose of the current or position of the current test image. This is the predicted position, predicted by the network. This is a position of the most similar training image. And ideally, what you want is that this predicted position is close to this to the ground truth position. But what actually happens is that the predicted pose is essentially always close to the training images, never to the test poses. And the reason for this is simple. As I said, the network learns a set of base poses. And since the training images are taken roughly on a line, the network essentially learns that all my base poses are roughly on the line. This is what is shown here. You see the position part of these base poses. And the color coding is warmer colors mean higher weight for the current test image. So you can nicely see that it has learned to do some sort of linear interpolation along a line, which obviously is going to fail if your data is not close to the line. So here we tricked the network into doing something like very simple because we gave it simple data. However, it turns out that even if you capture training images that should allow you to cover the space of all positions, this is not necessarily, it's still not able to generalize to new poses. So here, this is Prague Cathedral. We took a training trajectory that roughly goes around it, and then looked a bit at the other buildings here, and then had test trajectories that also looked into parts of the scene that was covered. If you visualize the position part of the base poses, this is for two networks, then you see that in both cases, the network has learned to place base poses roughly in a circle, which corresponds to the trajectory around the cathedral. And here, the color coding is base poses that are often part of training poses have a warmer color. However, if you try to predict poses for the test image, then you see that they're actually rather far away from the real positions and orientations, and instead they cluster around the training poses, maybe some sort of linear interpolation. And the reason is that in theory, you should be able to express the position and orientation as a linear combination of these base poses. But these base poses are also linked to image appearance through the embedding. So you are never going to be able to access all base poses for each test image, but you have a subset of them. And this subset turns out to be not large enough to be able to predict poses from new viewpoints. Last example that we did was trying to train with more data. So we did a synthetic experiment. Here what you see is the red pyramids are the original training images. Green pyramids are the original positions and orientations of the original test images. We used the training and test images to build a 3D model of the scene, and then rendered images of the 3D model from the original images, plus some additional poses that we placed, I think, 0.5 meter or apart, close by to the training and test poses. So essentially, you're creating much more data, meaning you have more training data that might help the network to generalize. So here are some results. What we show here is median position and orientation error in meters and degrees. For the original 203 training images, this is a post-regressor, has a median error of 1 meter, not too good. This is a retrieval system that is just doing interpolation between the top retrieved images, which is better than this method that's actually trained to predict poses accurately. And the last one is a structure-based method, like a type of method that I'm going to talk about later, which is orders of magnitude better. As you can see, both post-regression and the retrieval method benefit from more data, but they're still have a much higher error than a simple structure-based method that uses an order of magnitude less data. So the takeaway here is that contrary to many other fields in computer vision and artificial intelligence, visual localization seems to be a field where simply training a neural network to predict the quantity that you're interested in does not seem to be enough. You still need some sort of domain knowledge that you need to incorporate in a meaningful way, and the domain knowledge here is encoding something about scene geometry. So let's look at a second set of visual localization approaches, which are based on 3D scene representations. A classical approach is to build like a 3D model of the scene using things like structure for motion or simultaneous localization and mapping, where you essentially build a sparse point cloud, where each point is reconstructed from image pixels, and you can associate a local feature descriptor that describes the image patches around the pixels that we use to create the 3D points using some high dimensional vector. If you have a test image, you can also extract features and then establish 2D, 3D correspondences by comparing these local patch descriptors. And then you estimate a camera pose such that as many 3D points as possible project close to their 2D measurements. I call this classical methods because many of the individual parts are quite old. So the feature descriptors from the 90s, SIFT, for example, and pose estimation strategies go back to the 1700s, which are the first mentions of solvers that allow you to estimate a camera pose from 2D, 3D correspondences. A more modern approach is one that goes away from explicitly establishing 2D, 3D matches by extracting features and matching descriptors, and instead trains a CNN that for each pixel or each patch in an image predicts a corresponding 3D scene coordinate in the world. And these are typically end-to-end learnable, so ideally a much more powerful approach. And there's a couple of common beliefs in literature, which is classical methods based on experiments that people did do not seem to work well indoors because you find very few features. These coordinate regressors that use a CNN to predict 2D, 3D matches are actually better than feature-based methods. And if you get depth data as well, then you're typically better as compared to not using depth data at all. But it turns out, and this is a paper that we presented at ICV last year, that these conclusions are actually not necessarily correct. They were all, as I said, drawn from experimental results. So let's have a closer look at benchmarking localization systems. So ideally what we want is, given a pose predicted by some algorithm A, we would like to compare it against ground truth by measuring the distance between the camera positions and the camera orientations. The question is, how do you actually get the ground truth? So what we want is like a 6 vector where one part describes the position, one part the orientation. But humans, so one option would be to ask humans to label this, but humans are not really good at predicting this type of abstract representations. They could annotate correspondences between images, and then you could try to compute them using some algorithm, but even that is not easy and doesn't really scale. You could use sensors. For example, you could use a Vicon system indoors, but this also doesn't really scale well to if you want to capture many scenes, because it can be hard to set up and calibrate. So what people in the end do is they use some algorithms for structure for motion or simultaneous localization and mapping to create pseudo ground truth poses. So localization benchmarks actually measure how well an algorithm is able to replicate the method that generated the pseudo ground truth, and not really how accurate it is with respect to real ground truths. The natural question is, how important is it is actually the choice of algorithm that are used to generate the pseudo ground truths. In this paper, we looked at two ways to generate pseudo ground truths. One based on optimizing some error in 3D, so for example, depth-space SLAM systems, and one based on optimizing a 2D reprojection error between a 3D point and its corresponding measurement in images, so for example, structure for motion. And we showed that the way that the pseudo ground truth is generated can actually have quite a impact on the performance measured on a benchmark. So what you see here is like geometry of the scene, the pseudo ground truth poses predicted by depth space SLAM system, and the camera poses predicted by a feature-based, classical feature-based method that by now is about 10 years old. And what you see here is the projection of this model into the corresponding test image. And so this is the result that used to be there in the literature, and the argument was that, well, there's not much texture in the scene, you find few features, you can't compute an exact pose. However, if you recompute the ground truth using structure from motion, so meaning just based on images, not using depths, and applying the same algorithm, you got much better poses that are much closer to the ground truth. And this is the case even though you have few features and you have untextured features. Here's another example. Again, both types of ground truths, one computed using depth information, one just computed from color. And what we evaluated here is a state-of-the-art scene coordinate regression technique that uses RGBD images, the images with color and depth, not just color. And what you can see here is if you compare it against this classical baseline that only uses images on ground truth that was generated using depths, then this modern method that also uses depths is much better. If you compare it again on this ground truth that was generated using just images, then this classical method is better than this modern method, which is actually not what you really would like to see, because ideally, a benchmark should allow you to compare methods, and you should be able to draw an objective conclusion that one is better than the other. Whereas what we show is that whether an algorithm is better than the other actually depends a lot on the way the pseudo ground truth is generated, which naturally begs the question whether one pseudo ground truth might actually be better than the other, in which case we should just focus on one. So let's look at this question, which pseudo ground truth is actually better. What we show here are structure for motion point clouds. So structure for motion, as I said, generates a sparse point cloud from features extracted in the images. And here we just visualized the structure for motion point clouds generated using structure for motion pseudo ground truths and the pseudo ground truths generated using depth images and not features. And unsurprisingly, the structure for motion point clouds generated by structure for motion are better than those of the other pseudo ground truths. Unsurprisingly, in the sense of that this is what's optimized in the structure for motion ground truths, but not in the other one. If you look at the depth maps that are also available for the scene and just fuse them using the two type of poses, which is essentially closer to what this depth-based pseudo ground truth does. It's aligning depth maps so that they geometrically fit. Then we can also observe a couple of things. So we observe that globally, the structure for motion pseudo ground truth is more accurate. It's not as bent and gives you more details on objects that are far away, because this is the part of the scene that was mostly used to generate the poses. But also if you look at the foreground and more detailed objects, then you see that the depth space SLAM system gives you like a more clear reconstruction. And this is something that we consistently observed. So here's another example of another scene where the global structure is a bit bent when you're just using depths or depths and color, versus you get better structure using structure for motion. But if you look at details, then they are more preserved in this depth-based ground truth. So our conclusion was that there's actually no clearly better pseudo ground truths. Both are valid. Both should be considered. And I'm not going to go into comparisons here, but what we essentially showed that all these statements, classical methods do not work well indoors, coordinate regression outperforms feature-based methods, depth-based methods outperform color-based methods, are correct or wrong depending on which pseudo ground truths you choose, to the degree that we could complete or nearly completely invert rankings if we chose a different pseudo ground truths. So in essence, what we showed is that the way that pseudo ground truth is generated is important because some algorithms are closer to the algorithm that generated pseudo ground truths than others, and they have a much easier time recreating the camera poses of the pseudo ground truths. A natural approach out of this would actually be to use synthetic data, given that we can nowadays build like photorealistic reconstructions of the world. But I don't think that it's that easy. So here are two images of the City Hall in Aachen, and here's a set of feature matches between those two images. So a state-of-the-art feature matcher found about 1,000 matches between them. Here's the same two images re-rendered using a 3D model created from a state-of-the-art 3D reconstruction pipeline. So as you can see, there are some ghosting artifacts here in the sky, but the 3D geometry that is reconstructed very accurately and looks photorealistically. Interestingly, if I match features, like the same type of features between those two images, I get roughly 2 times more matches. And I think what's happening here is that there's a certain amount, like there's differences in low-level statistics that are not visible to the human eye, but that these local features pick up on. And that makes feature matching between synthetic images much easier than between real images. And since feature matching is essentially, like this data association problem is essentially the main problem in localization, just using synthetic data might not give you a good answer. Okay, so the takeaway from this part is that the structure-based methods enable accurate localizations, to get accurate camera poses, but we currently don't know which strategy works best. So using local features as in classical methods versus training CNNs to regress camera poses, scene coordinates. And as I mentioned before, we might not be able to actually objectively answer this as it really depends on the pseudo ground truths used to generate the benchmarks. These were the main points that I wanted to make. Let's finish with a couple of open problems. So one problem in localization, but also mapping, is actually modeling interactions. So here you see this system that I showed before in action, where we track the human pose, and the human is actually interacting with the world by taking a book out of the shelf. But because our scene representation is static, we're actually not able to model this interaction. Here's another problem that can happen if you have static maps, is that this is the images taken after the 3D model was built, and in between this table was moved. So this is why the human is actually able to walk here, but in this virtual model, in this digital twin, if you want, there is an obstacle. And if you start reasoning about or trying to integrate scene constraints such as humans should not walk into walls and so on in this pose-tracking approach, then you might run into problems because there's geometry where it shouldn't be, meaning your algorithm might try to give you a wrong answer because it tries to avoid the human walking through where it believes an object is. Another problem is repetitive scenes. So here's the human looking at these information sheets at the library. They all look rather identical. So localization actually jumps in between those few pillars. And then the human is moved because we have the smoothness term between the localization results that enforces the human to move smoothly over time. But figuring out, like, resolving this is a hard problem. So imagine that your corridor in your offices, which are typically very repetitive, and then showing an image of this, and it's really hard to figure out where in this corridor it was actually taken. Another open problem is long-term localization, where this is 3 images of the same place taken at different seasons and different weather and illumination conditions. And you can see that the appearance of the scene, especially of the vegetated part, can change quite drastically. And data association between those images is a hard problem, and solving it is important if you want to have, say, robots that operate in forests or would like to play augmented reality games in parks, or you would like to build a robot that can operate in any condition and under potentially outdated maps. And solving this, I think, will likely require some form of scene understanding. Okay, to conclude, I hope I convinced you that visual localization is an important and interesting problem with many applications. What I like about it is that compared to other areas of artificial intelligence or computer vision, the simple machine learning solution of training a neural network does not seem to work that well. But current state-of-the-art methods still rely on classical concepts of 3D geometry. And I hope I convinced you that there are still many interesting problems in this area that are worth solving and that should be solved. Thank you very much. If you have any questions, now is the time to ask.
Thank you very much, Torsten, for a very nice